In the first workshop, we will model a cantilever beam made of AISI 1010 steel in which a pressure load is applied on its top face. We are going to model this beam once with just elastic properties and another time by both elastic and plastic properties. The pressure magnitude for the first model is 2.0 megapascal and for the second model is 2.5 megapascal. The elastic and plastic properties are shown here. We use the Johnson-Cook strength model for calculating the equivalent 1 mices. Constant A is the yield stress corresponding to a 0.2% offset strain. Constant B and exponent N represent the strain hardening effects of the material. We should fill out the table in the plastic section in property modules by stress and equivalent plastic strain. The beam has a length of 300 mm and a rectangular cross-section 120 mm wide and 200 mm high. Here in the ABAQUS CAE graphical interface, we do modeling of the part, and after that we use .jnl file as initial script to do more practice. Here we should submit the job to have JNL file in the desired directory. Considering that the analysis steps in the software are completed, So open the journal file in the working directory in a text editor such as Notepad++. In order to be able to make changes in this written code and write the script we want, we have to copy all the code and paste it into a Python file. We begin the script using a couple of from import statements. The first import statement is import ABAQUS. Imports the ABAQUS module and create references to all public objects defined by that module. Thus, it makes the basic ABAQUS object accessible to the script. For example, default model database, which is called with the mdb command, is accessible using this import statement. You use this variable mdb in the next block of code, which is the create model block. You need to insert this import statement in every ABAQUS script you write. The second import statement is for making the symbolic constants defined by the ABAQUS scripting interface available to the script. The following block creates the model name beam. Then we should introduce some variables to reduce the repetition in code as well as making it more readable. For example, here we introduce my model to the first line, because in the next line we have to call the model by the mdb.models beam statement. The difference between commanding a model and calling is that the first letter of the command is written in uppercase and that one is in the lowercase, and also the last letter of the calling command is ended to an S that is not in the other one. The pattern for the building and calling is almost the same for all these commands. This second statement creates a constrained sketch object by calling the constrained sketch method of the model object. Remember that import the sketch and part module into the script, thus providing access to the object related to the sketch and parts. Thankfully, these statements are written in the first line of the journal file and we saw them before. Some of the method index one or more required or optional arguments. For example, here the first argument is that the name you wish to give the sketch, and the second argument is the default sheet size, which is a property you defined when manually performing the cantilever beam simulation in ABAQUS CAE. The base solid extrude method is used to create extrusions. Here our sketch is deleted, which does not need to be done, and we can delete this line. We introduced a variable for all components made in ABAQUS, including sketch, material, section, assembly, and so on. To introduce variable for material, we can use the Ctrl+F shortcut. And then click on replace, so here we can change the variable name for the entire code. This statement creates a homogeneous solid section object. All given properties, including dimensions, material property, and so on, are according to the presentation. The following code block creates the set and makes section assignments. We don't need this block of code, of course. That's because firstly, we don't need to create sets. Secondly, in this block of code, the journal file used the getSequenceMask statement for determining the part cells. This method returns the object or objects in the face array, edge array, cell array, or vertex array was identified using the specified mask. Furthermore, a string specifying the object or objects that we do not know that, so we should find out these strings by try and error. Therefore, we comment on this block. Instead, we can use the cell method to find the cells of the beam. The cell object defines the volumetric regions of a geometry. So notice that there is a comma after beam part.cells. This is because we are trying to create a variable that is a region object. You can use a region object to define the geometry for a section assignments or a load or a boundary condition or a mesh. Basically, it forms a link between the geometry and the applied attribute. After that, we index the part region as a region argument in section assignment method. This is a small part of the Python scripting in ABAQUS training package. There is a lot more valuable information in other parts of this package that you can get on our website. We suggest you do your project by saving your time and getting basic training so that you don't get tired of ABAQUS errors. The following blocks create the assembly and the steps. These lines of code determined the boundary conditions. So again, we need to define a region for that. The journal file creates a set by using the getSequenceMask statement as before. Hence, we comment on this block of code and write the following lines. We use find_at method instead. Find_at returns the object or objects in the face array, edge array, cell array, a sequence of floats specifying the x, y, and z coordinates of the object to find. and vertex array located at the given coordinates or a distance of less than 1e minus 6 from it. We use find at because we don't know the string specifying the end face, but we know the coordinates of it. For the record, if the point is shared by more than one face, the method will return whichever face encounters first, and there is no way of predicting which one it will be. Again, we make it a region by putting this to a tuple, the following block applies the loads. When we want to locate the face to which pressure will be applied, we should determine which side of the face should be used. When we set side 1, the normal of the region is the same as the normal of the face. If instead we had written side 2, the normal to our region would have pointed into the beam rather than out of it. Here we should convert these lines to comment as before. So I have already written the related codes in this file, and I just copy and paste them here. Then change the necessary items here. The following block creates the mesh. These lines which define the element type of mesh are unnecessary because we only need C3D8R type for elements, so we replace them with these two lines of code here. This method creates an element type object. An element type object is an argument object used as an argument in the setElementType command. The setElementType required only two objects. Region, that is a sequence of geometry regions or mesh element objects. Specifying the regions to which element types are to be assigned. And element types, which is a sequence of element type objects, one for each element shape applicable to the regions. After generating the mesh, the following block runs the job. This statement submits the job for analysis. The submit method is a method for the job object. It has no required arguments, although it does have a few optional ones. The next lines are for showing messages in the monitor which are now useless for us, so we delete them. So far, we have only made some changes to the appearance of the script. To go a little further than what we did, I have created another Python file on which I have written the same code with all the correction made on them. As you can see, the code is modified here, plus the phrase viewport, which is used to create a viewport with the given specifications. Here we want to determine the plastic properties of the material according to the presentation slide. The command to specify plastic is similar to the command to elastic. We just have to write plastic instead of elastic. To do this, we need to import numpy module, because we need the arrange function to create a range of floating numbers. Numpy is a module that enriches the programming language Python with powerful data structures, implementing multi-dimensional arrays and matrices. Then we define the constant of the Johnson-Cook plasticity model. We create an empty list named sigma, which will be filled in for loop by tuples of von Mises, flow stress, and the equivalent plastic strain. The arrange function returns an array with equally spaced elements as per the interval, where the interval mentioned in is half opened. The first parameter is a start. It is an optional parameter that represents the start of the interval range. By default, the value of start is 0. The second parameter is a stop. This parameter represents the end of interval range. The third parameter is a step. It is an optional parameter representing the step size of the interval. By default, the step size is equal to 1. We write print function here to see the result of these calculations in the message area of GUI. After the sigma list is created, we convert it to a tuple since the table argument is in the plastic method only accepts tuples. The rest of the code is the same as what we explained before, except this part that we add wait for completion method of the job object. This statement makes sure the control lies with the script till the analysis finishes executing. We also write these lines to visualize the results. This statement creates the ODB object by opening the output database, whose path is provided as an argument, and assigns it to the variable myODB to show that how to use the documentation to find out how to use method. I take OpenODB method example. You can follow these steps as stated before. As you can see, it required name only. Note that we have not provided a complete path, only the file name. Hence, it will search for the file in your working directory. You may provide an absolute path if you are working with an output database file saved elsewhere on the hard drive. This statement uses the setValues method to set the display to the selected output database. This statement changes the viewport display to the deformed beam. By using the setValues method and setting the plot state to the symbolic constant contours underline on underline def. We also increase the magnitude of pressure to see the plastic deformation well. Finally, we run this script to see our simulation. As you can see, these numbers and tuples are printed here as a result of a print function that we added to our code. You can see that our model is entered to plastic deformation area because we have valued the equivalent plastic strain. This workshop is over now, and I hope you enjoy scripting in Python. This is a small part of the Python scripting in ABAQUS training package. There is a lot more valuable information in other parts of this package that you can get on our website. We suggest you do your project by saving your time and getting basic training so that you don't get tired of ABAQUS errors.